Here is example 1-12. It talks about capillary rise, and we are asked to find what the length of this of the rise is in an inclined tube, and we're asked to do that based on the diameter of the tube, the angle of the inclination, also the surface tension of the water sigma, and the density rho. So in order to do that, we will start with writing a free body diagram. Free body diagram. We'll do that for kind of the water that is in the little pipe that we're interested in. So one thing that we can do is we know that we have the capillary forces are trying to hold the water upward, right? They're along the diameter of our little pipe. So we'll just put them going straight up because they're holding it along the pipe. And we'll call that FC for capillary. We'll also have the weight of the water, of course, going straight down. And let's not forget that we also have our angle. Put that angle in there. Angle theta. Now, before we write our free body diagram, let's break apart our weight vector into something that's perpendicular to the pipe and also a component that's parallel to the pipe. And of course, we know that that angle there is again going to be theta. So I think now we have everything to write our free body diagram, to write our force balance. So we can say we can sum the forces in the parallel direction of the pipe, so going along the pipe. We know that has to be equal to 0 because it's not moving. So what do we have? We have FC, let's define that as positive. And then we have a component of the weight that is in the other direction, right? That'd be this component right here. The angle is there, so it's going to be times sine theta. Then we can plug in what we get for FC, right? We know that would be the surface tension times the diameter of the pipe. So that would be sigma times not the diameter, the circumference, pi times z, that's the circumference. And then the weight of the water is just going to be the volume times the density times gravity. So volume would be the area, cross-section area would be pi over 4 d squared times the length. That's what we were interested in. So that would be the volume. Then we multiply that by the density times g times our sine theta. So now all we have to do is we have to start solving this for L, right? So we could say pi over, not over d, but over 4. Pi over 4 times d squared times L times rho times g times sine theta would be sigma pi d. You can already see that some of this cancels out, right? We see we have a d here. We cancel that out with a square, and we can cancel out the pi's. So then for the rest, we can solve it for L. And that means L is equal to here. On the other side, so we multiply by 4. So we'd have 4 sigma. And we divide that by what's left. The D is left. The L is over there. Rho times G times sine theta. And there we are. That's our length. Right? Does it make sense? Well, as the larger our surface tension is, the higher it's going to be pulled up. That makes sense. The smaller the tube is, the bigger it's going to get pulled up. The larger the density is, the more it's going to stay in there. And of course, the larger our sine theta is, so the larger the angle is, the less far it's going to be pulled up into the pipe. All right, so all these make sense. So this was the derivation of the height within an inclined pipe with capillary rise.